Hello. In my part of the lesson, I'm going to talk about the graphing form of the quadratic equation in two variables. When the equation is written in this form, several aspects of the graphing process become very simple. I'm first going to consider equations of the form y equals x minus h quantity squared plus k, and then I'm going to add a non-1 coefficient in front of the x minus h quantity squared term of the expression. Let's find the vertex of the parabola with equation y equals x squared plus 8. Well, recall that we can get the x-coordinate of the vertex using the formula x equals opposite b over 2a. b is the coefficient on the linear term. I don't see a linear term in this formula in terms of x. But remember, I could rewrite the x expression as x squared plus 0x plus 8, and that shows me that the linear coefficient is 0. So the x-coordinate of the vertex is x equals the opposite of b, so that's the opposite of 0, over 2 times a, so that's 2 times 1, and this just simplifies to 0. But remember, the vertex is a point in the coordinate plane, so I need a y-coordinate as well. When x equals 0, y equals 0 squared plus 8, which is just 8. The vertex is the point 0, 8. Do you see 8 in our equation? Well, sure. 8 is the number that's being added to x squared. Let's find the vertex of the parabola with equation x squared minus 2. Again, the x-coordinate is given by the formula opposite b over 2a. And again, I can think of this equation as y equals x squared plus 0x minus 2. So the x-coordinate of the vertex is x equals the opposite of 0 over 2 times 1, which is still 0. But again, the vertex is a point in the coordinate plane, so I need a y-coordinate as well. When x equals 0, y equals 0 squared minus 2, which is negative 2. So this gives us that the vertex is the point 0, negative 2. Well, I don't see negative 2 per se in my equation, but I could rewrite my equation as y equals x squared plus negative 2. So once again, the y-coordinate of the vertex turned out to be the number that's being added to x squared. So let's summarize the last couple of examples. The vertex of the parabola y equals x squared plus 8 is the point 0, 8. The vertex of the parabola y equals x squared plus negative 2 is the point 0, negative 2. I see a pattern. The pattern seems to be that the vertex of the parabola y equals x squared plus k is the point 0, k. Let's look at a slightly different type of equation. This time we want to find the vertex of y equals x minus 4 quantity squared. Again, thinking about my vertex formula for the x-coordinate, I need to have my equation written in standard form so that I can identify the coefficients a and b. So the first thing I need to do is I need to take my equation y equals x minus 4 quantity squared, and I need to FOIL so that I have the right side of the equation in standard form. I'm going to think about x minus 4 quantity squared as x minus 4 times x minus 4. So that gives me y equals, well, my f's are x times x, which is x squared. My o's are x times negative 4, and my i's are negative 4 times x, and that all adds up to minus 8x, and my l's are plus 16. So now I can identify a and b, so the x-coordinate of the vertex is x equals the opposite of negative 8 over 2 times 1. That's the opposite of negative 4, which is positive 4. I need the y-coordinate too, though. When x is 4, y is 4 minus 4 quantity squared. The square of 0 is just 0. So this time, the vertex is the point 4, 0. Do you see 4 in the equation? Well, sure you do. 4 is what's being subtracted from x before that expression is squared. How about y equals x plus 2 squared? Before I can use this formula, I need to have my equation written in standard form. Y equals x plus 2 quantity squared. I think I'm going to use one of my special forms to figure out what x plus 2 quantity squared is. My special form says that when I square a binomial that's being summed, I need to take the first term squared, so that's x squared, and then I need to add to that the product of 2 times the product of each of the terms. So that's 2 times x times 2, which is 4x. And then I need to add the last term squared. So that's plus 4. So this gives me that the x-coordinate of the vertex is x equals the opposite of 4 over 2 times 1, which is negative 2. Well, what's y when x is negative 2? When x is negative 2, y is the square of negative 2 plus 2. Negative 2 plus 2 is 0, and 0 squared is still 0. So the vertex is the point negative 2, 0. Now this time in my equation, I don't see negative 2 in any sense of the word. But there is a way I could rewrite my equation so that I did see negative 2. And that's that I could rewrite it as x minus negative 2 quantity squared. So let's review the last couple of examples and see if we see a pattern. The vertex of the parabola y equals x minus 4 squared is the point 4, 0. The vertex of the parabola y equals x minus negative 2 squared is the point negative 2, 0. I see a pattern. It seems that the vertex of the parabola y equals x minus h quantity squared is the point h, 0. I wonder if we can take these two observations and put them together. I've got a kind of fancy little doodad graph here that graphs equations of the form y equals x minus h quantity squared plus k. Right now, the value of k is set at 0, and the value of h is set at 0. So what I'm looking at is a graph of y equals x minus 0 quantity squared plus 0, or just y equals x squared. 2, 4. 4 is 2 squared. 4, 16. 16 is 4 squared. Now what I'm going to do is I'm going to have the computer increase the value of k from 0 up to 8. And what I want you to do is watch what happens to the parabola, and specifically the vertex of the parabola, as k increases to 8. As k increases, the vertex goes up. And the vertex of the parabola y equals x minus 0 squared plus 8 is the point 0, 8. Now what I'm going to do is I'm going to take the value of h and I'm going to shift it over to 4. And what I want you to do is watch what happens to the vertex of the parabola as h increases to 4, as h moves to the right along the number line. The vertex of the parabola moves right along with h. And in fact, the vertex of the parabola, y equals x minus 4 quantity squared plus 8, is the point 4, 8. Now I'm going to take h and I'm going to move it to the left along the number line. I think I'm going to move it to negative 2. Let's see what happens to the vertex of the parabola. It moves right along with h, and I end up with the vertex of the parabola y equals x minus negative 2 quantity squared plus 8 is the point negative 2, 8. I wonder what it would take to move this vertex down to the point negative 2, negative 2. I bet you I need to decrease the value of k from 8 down to negative 2. Let's do that. Sure enough, the vertex of the parabola y equals x minus negative 2 quantity squared plus negative 2 is the point negative 2, negative 2. It turns out that our two facts do work together. The vertex of the parabola y equals x minus h quantity squared plus k is the point hk. Let's do a little exploration in a table to see if we can get an understanding of why it works out this way. What I'm going to do is I'm going to create a table for y equals x minus 4 quantity squared plus 8. I'm going to show a couple rows between the values of x and y so that we can develop an understanding of why the vertex of this parabola has to be the point 4, 8. Let's start in the column where x is 4. Well, when x is 4, the value of x minus 4 is 0, and 0 squared, x minus 4 quantity squared, is also 0. So in my formula, I'm adding 8 to 0, which gives me 8. Well, if 4, 8 is indeed the vertex, since we know the vertex lies on the axis of symmetry, it has to be the case that x equals 4 is the axis of symmetry. Well, if x equals 4 is the axis of symmetry, looking on my number line, when I go 1 unit to the left and right of x equals 4, I should get the same value of y at each of the points on the parabola. So when x is 3 and x is 5, I should get the same value for y. Why does that happen? Well, again, let's look at these middle two rows. When x is 3, the value of x minus 4 is 3 minus 4, which is negative 1. When x is 5, x minus 4 evaluates to positive 1. Well, what are we doing with x minus 4? We're squaring it. And it doesn't matter whether you square negative 1 or positive 1. In both cases, the result is 1, and adding 8 to 1 gives us a y-coordinate of 9. Indeed, when we go 1 unit left or right of x equals 4, we get the same y-coordinate. How about if we go 2 units left and right of x equals 4? Well, 2 minus 4 is negative 2, and 6 minus 4 is positive 2. What are we doing to those numbers? We're squaring them, and if you square negative 2 or positive 2, the result is 4. Adding 8 to 4 gives us a y-coordinate of 12 at both x equals 2 and x equals 6. It is indeed true that x equals 4 is our axis of symmetry. Let's see it one more time. Let's go 3 units left and right of our axis of symmetry. Now, when x is 1, 1 minus 4 is negative 3. When x is 7, 7 minus 4 is positive 3. The square of each of those numbers is 9, and when we add 8 to 9, we see that the y-coordinate at both x equals 1 and x equals 7 is 17. So let's go ahead and graph this parabola. When I graph this, I don't need the middle two rows. I just included those in the last table to help you understand why x equals 4 is our axis of symmetry. So let's get rid of those middle two rows, and let's introduce a grid so that we can actually graph. When I graph parabolas, especially when they're in graphing form, I like to graph from the vertex out, because then I can exploit symmetry to quickly plot points. So I have the point 4, 8 as my vertex. Then, when x is 3 or 5, the value of y is 9. When x is 2 or 6, the value of y is 12. When x is 1 or 7, the value of y is 17. Let's check out what y is when x is 0. When x is 0, the value of y is negative 4 quantity squared plus 8. That's 16 plus 8, which is 24. 0 is 4 units to the left of x equals 4. 4 units to the right of x equals 4 will give us an x-coordinate of 8, so our parabola must also have the point 8, 24. Now I can see clearly I'm going to go off my grid if I go any farther out. So let's go ahead and sketch our parabola. Let's graph this parabola. Candace referred to this as the vertex form of the quadratic equation. The reason she did that is because one of the things it's really easy to do when your equation is written in this form is to find the vertex. So what is the vertex of this parabola? Well, let's rewrite the equation in the form y equals x minus h quantity squared plus k. That would be y equals x minus negative 1 quantity squared plus negative 4. Then the numbers h and k form the coordinates of the vertex. The vertex is the point negative 1, negative 4. So now let's fill in a table. When I fill in a table, I like to put the vertex kind of in the middle of the table. So I'm going to make the middle column here, x is negative 1, when y is negative 4. Now I'm going to increase the x-coordinates by 1 to the right and decrease the x-coordinates by 1 to the left. So the right side, I'm going to look at x equals 0, 1, and 2. And the left side, I'm going to look at x equals -2, -3, -4. I'm going to fill in the right side of this table first. When x is 0, y is 0 plus 1 quantity squared minus 4. That's 1 squared minus 4. 1 minus 4 is -3. When x is 1, y is 1 plus 1 quantity squared minus 4. 2 squared minus 4 is 4 minus 4, which is 0. When x is 2, 2 plus 1 is 3. 3 squared minus 4 is 5. I don't need to do any computations to the left. I know that x equals -1 is my axis of symmetry, so at -2, y is -3, at -3, y is 0, and at -4, y is 5. So here's my grid. Looking at my points, my vertex has an x-coordinate of -1, which is pretty close to the y-axis, so I'm going to draw my y-axis pretty much in the middle of my grid. Likewise, looking at the y-coordinates in my table, the distance between the extreme y-coordinates and 0 is pretty much the same in both the positive and negative direction. So I'm going to put my x-axis pretty much in the middle of my grid. Now I need to go ahead and label my axes. This is the x-axis, this is the y-axis. I think a scale of 1 is going to work pretty well in both the x-axis and y-axis. So this is going to be 2, 4, 6, -2, -4, -6, 2, 4, 6, -2, -4, -6. Now I can set about to plotting my points. Again, I find it quickest to plot from the vertex out. So our vertex is the point -1, -4. 1 unit to the left and right of the vertex, y is -3. 2 units to the left and the right of the vertex, y is 0. And 3 units to the left and right of the vertex, y is 5. I'm pretty sure I'm off my grid if I go any farther out in terms of integers, but I am going to check. When x is 3, what do I get for y? I get 4 squared minus 4, which is 16 minus 4, which is 12, which is well off our grid. So let's go ahead and connect our points. Let's graph y equals x squared minus 6x plus 4. We showed you several steps that you can follow to get a good graph of a parabola written in standard form. I'm going to take a slightly different tack. I am going to begin by finding the vertex. And I can find the x-coordinate of the vertex using the formula x equals opposite b over 2a. So the x-coordinate of the vertex is x equals the opposite of -6 over 2 times 1. That's the opposite of -3, which is +3. And when x is +3, y is 3 squared minus 6 times 3 plus 4. So let's see, that's going to be 9 minus 18 plus 4, which is -5. So the vertex is the point 3, -5. Now what I'm going to do with that vertex is I'm going to go ahead and rewrite my equation in graphing form. And the reason I'm going to do that is because it's really easy to calculate additional points when the equation is written in graphing form. So the graphing form of this equation is going to be y equals x minus the x-coordinate of the vertex, so that's x minus 3 quantity squared plus the y-coordinate of the vertex, which is -5. So this simplifies into y equals x minus 3 quantity squared minus 5. I am going to simplify by foiling this expression to make sure that I really do get y equals x squared minus 6x plus 4. So if I take x minus 3 quantity squared and subtract 5, using my special products, this is x squared minus 2 times x times 3, which is 6x, plus 9, minus 5, which does simplify to x squared minus 6x plus 4. So my graphing form checks. So let's go ahead and make our table. But let's use our graphing form. Our vertex is the point 3, -5. So to the right of x equals 3, I'm going to check out x equals 4, 5, and 6. And to the left of x equals 3, I'm going to check out x equals 2, 1, and 0. When x equals 4, looking at my graphing form, y is 1 squared minus 5, which is -4. When x equals 5, looking at my graphing form, y is 5 minus 3, quantity squared, minus 5. That's 2 squared minus 5, which is -1. When x is 6, 6 minus 3 is 3. 3 squared minus 5 is 9 minus 5, which is 4. Now I can get points to the left of the vertex using symmetry. We must have the point 2, -4, 5, -1 gives us 1, -1, and 6, 4 gives us 0, 4. So let's graph. This time, the x-coordinate of the vertex is far to the right of the y-axis. So I'm going to draw my y-axis very close to the left edge of my grid. On the other hand, I have a y-coordinate of 4 and a y-coordinate of -5. That's pretty equidistant from the x-axis. So I'm going to go ahead and draw my x-axis sort of in the middle of my grid. Let's label. This is the x-axis, this is the y-axis. Looking at the numbers, I think a scale of 1 is going to work well on both axes. So I have 2, 4, 6, 8, 10, and then here I have 2, 4, 6, -2, -4, -6. Let's plot our points. The vertex was the point 3, -5. Then we had the points 2, -4, and 4, -4. We had the points 1, -1, and 5, -1. We have the points 0, 4, 6, 4. I wonder what happens when x gets up to 7. Well, let's recall our graphing form. If I replace x with 7, inside those parentheses I'll have 4. 4 squared minus 5. That's 16 minus 5, which is 9. We're off the grid. If we're off the grid at x equals 7, we're also off the grid at x equals -1. So let's go ahead and connect our points. You know, if you're having trouble drawing these parabolas, I hope you're getting a nice object lesson that I have some trouble drawing them as well. These are kind of tricky to draw. You know, something that we might ask ourselves about this parabola is, what are the x-intercepts? Well, the graphing form of the equation actually even makes this question easy to answer, because the x-intercepts are where y equals 0. And when y equals 0, using our graphing form, we have x minus 3 quantity squared minus 5 equals 0. So now I can say that x minus 3 squared equals 5, and I can use my square root property that tells me that x minus 3 has got to equal plus or minus the square root of 5. So when I add 3 to both sides of this equation, I get that x equals 3 plus or minus the square root of 5. So our x-intercepts must be the points 3 plus the square root of 5, 0, and 3 minus the square root of 5, 0. What I'm going to do now is I'm going to explore parabolas where the coefficient on the x minus h squared term is something other than 1. Let's compare the graphs of y equals 1x squared, y equals 2x squared, and y equals 1/2 x squared. Well, I have 3 parabolas on a grid, so presumably the 3 parabolas are corresponding to the 3 equations. Let's see if we can figure out which one is which. Well, with the equation y equals x squared, when x is 1, y is 1. When x is 2, y is 4. Do we see one of these parabolas that goes through 1, 1, and 2, 4? Well, sure, the one in the middle. So the one in the middle must be our y equals x squared parabola. Well, which parabola is y equals 2x squared? Well, on y equals 2x squared, when x is, say, 2, the value of y is 2 times 2 squared. 2 times 4 is 8. Which parabola has the point 2, 8 on it? That's the inside parabola, the narrowest parabola, the skinniest parabola. The skinny parabola is y equals 2x squared. So it must be the case that the widest parabola is y equals 1/2 x squared. Let's make sure. When x is 2, 2 squared is 4. 4 times 1/2 is 2. 2, 2. Sure enough, the outside parabola is y equals 1/2 x squared. Now, all three of these parabolas have positive values for a, if you think of a as the coefficient on x squared. And it appears that as a gets larger, the parabola gets more narrow. I wonder if that's always true. Well, what I've created here is a little slider system. Up here, I'm stating the value of a, and here I'm graphing the parabola y equals ax squared. Right now, a is set at 1, so we're looking at y equals x squared. Let's check that out. 2 squared is 4. 4 squared is 16. We're looking at y equals 1 times x squared. Let's see what happens if we reduce this value of a down to a value of 1/2. According to what we were just discussing, we should observe the parabola getting wider. Let's see if that indeed happens. Sure enough, it consistently got wider. Let's make sure that we are looking at y equals 1/2 x squared. When x is 4, 4 squared is 16. 1/2 of 16 is 8. Do we have the point 4, 8? 4, 8. We really are looking at y equals 1/2 x squared. Now, what happens if we push our slider up to 2? Well, according to what we observed, we should observe our parabola consistently getting more narrow. Let's see. Sure enough, as the value of a increases from 1/2 to 2, our parabola got consistently more narrow. Let's make sure we're looking at y equals 2x squared. When x is 2, 2 squared is 4. 2 times 4 is 8. 2, 8. We really are looking at y equals 2x squared. So when a is positive, the larger the value of a, the more narrow the parabola. The smaller the value of a, the wider the parabola. This is when a is positive. I wonder what happens when a is negative. Well, let's compare y equals the opposite of x minus 1 squared plus 3 and y equals negative 3 times x minus 1 quantity squared plus 3. Well, both of these parabolas have the form y equals a times x minus 1 quantity squared plus 3. So both of these parabolas should have a vertex at the point 1, 3. I've gone ahead and let the computer generate our parabolas, so we've got a nice picture. And notice that both of these parabolas do have their vertex at the point 1, 3. I wonder which parabola is which. Well, let's pick a value of x, calculate what y is, and then figure out which parabola goes with that. Let's look at this formula. Let's see what y is when x is, say, 2. So in this formula, when I replace x with 2, inside the parentheses, I get 2 minus 1, which is 1. 1 squared is 1. Negative 3 times 1 is negative 3. And when you add positive 3 to negative 3, you get 0. So this parabola passes through the point 2, 0. That's the skinny parabola. This inside narrow parabola is the parabola where a is negative 3, and this outside wider parabola is the parabola where a is negative 1. I can think of that opposite sign as a factor of negative 1. So what's the pattern here? Well, it's not just that when a is bigger, the parabola gets narrower. I think we need to look at the absolute value of a. The absolute value of negative 3 is larger than the absolute value of negative 1. So it must be the case that when the absolute value of a increases, the parabola becomes more narrow. Let's graph y equals 2x squared plus 12x plus 14. I'm going to perform this graphing procedure somewhat similarly to an earlier example. I'm going to find the vertex, and then I'm going to rewrite the equation in graphing form so I can easily pick off some more points on the parabola. So beginning with what's the vertex, using my formula, I see that the x-coordinate of the vertex is x equals the opposite of 12 over 2 times 2. 12 over 4 is 3, so the x-coordinate is negative 3. when x equals -3, y is 2 times -3 squared plus 12 times -3 plus 14. So doing some arithmetic in my head, this is 18 minus 36 plus 14. 18 and 14 is 32, and 32 minus 36 is -4. So it looks like our vertex is the point -3, -4. So now, what's the graphing form of this equation? Well, this time it's a little trickier than the last time because my leading coefficient on the x side of the equation isn't 1, it's 2. From my vertex, I know that I need to have y equals a times x minus -3 quantity squared plus -4. Well, when I FOIL this out, I know that the first term I'm going to get is x squared. And when I multiply x squared by a, I need to end up with 2x squared. So my value of a must be 2. This must be y equals 2 times x plus 3 quantity squared minus 4. But I better check. When I take 2 times x plus 3 quantity squared minus 4, I get 2 times x squared plus 6x plus 9 minus 4. So that's 2x squared plus 12x plus 18 minus 4, which is 2x squared plus 12x plus 14, which is my given equation. So my graphing form's correct. Here's my table. Here's my graphing form. The vertex is -3, -4. So I'm also going to check x equals -2, -1, 0, and use symmetry to get the points where x is -4, -5, and -6. Replacing x with -2 in the graphing form, I'm going to have 2 times 1 minus 4, which is -2. Replacing x with -1, I'm going to have 2 times 4 minus 4, which is 4. And replacing x with 0, I'm going to have 2 times 9 minus 4, which is 14. Let's use symmetry to fill in the rest of the table. Here's my grid. The x-coordinate of the vertex is far to the left of the y-axis. So my y-axis this time is going to go far to the right side of my grid. Looking at the y-coordinates, the lowest y-coordinate is -4. The largest y-coordinate is 14. 14's a heck of a lot farther from the x-axis than -4. So I want my x-axis close to the bottom of the grid. Labeling x and y, once again, a scale of 1's going to work just fine on the x-axis. But if I want to get clear up to y equals 14, I think I better use a scale of 2 on my y-axis. Let's plot my points. My vertex is -3, -4. When x is either -4 or -2, the value of y is -2. When the value of x is either -5 or -1, the value of y is 4. When the value of x is 0 or -6, the value of y is 14. When x is 1, what's the value of y? Well, it's 2 plus 12 plus 14, which is 28, which is way off our grid. So we're off our grid at x equals 1, so we must also be off our grid at x equals -7. So let's connect our points. You know, every once in a while, even I draw a pretty darn good-looking parabola, and that was the once it's going to happen all term. Let's summarize. The vertex of the parabola y equals a times x minus h quantity squared plus k is the point hk. The parabola y equals a times x minus h quantity squared plus k opens upward if a is greater than 0 and opens downward if a is less than 0. When graphed on a common grid, the parabola y equals a times x minus h quantity squared plus k is wider than the parabola y equals b times x minus h quantity squared plus k if the absolute value of a is less than the absolute value of b. Equivalently, The parabola y with the a coefficient would be narrower than the parabola with y equals the b coefficient if the absolute value of a was greater than the absolute value of b. And that's it for my part of the lesson. Now Anne is going to find some equations from the graph.
In this last part of the lesson, what we're going to do is start with a graph of a parabola and come up with an equation that describes the parabola. I'm going to start by working several examples, and then at the end we'll summarize the strategy that we've used to determine these equations. So here's an example. Determine an equation for the parabola graphed in Figure 1. We just have this picture of a parabola. We want to know the equation. Well, Steve was just describing the graphing form or vertex form for the equation of a parabola. When I look at my graph here in Figure 1, I can read the coordinates of the vertex right off the graph. I know h equals 3 and k equals 4. I can just substitute those values into vertex form. So I have y equals a times x minus 3 quantity squared plus 4. Now I have just one last thing to figure out. What's the value of a? Looking at the graph, I know a must be negative, but that's about all I know about a right from the get-go. But what I do know is I know some other points on this graph. For example, I can see that the vertical intercept is the point 0, 2. When x equals 0, y equals 2. I'm going to use this to determine a. So since y equals 2, when x equals 0, I'm just going to plug that into my equation. I have 2 equals a times 0 minus 3 squared plus 4. Hopefully you can see why this is going to allow us to figure out a. I only have one unknown in this equation. I should be able to solve for a. So I have 2 equals 9a plus 4. So 9a equals negative 2. So a equals negative 2/9. So it seems that the equation for that parabola could be y equals negative 2/9 times x minus 3 squared plus 4. But I want to perform a check. So here's my equation and here's my parabola. Now what I have here is another point on the parabola that I got from using symmetry, the point 6, 2. So I want to check whether or not the points on the parabola satisfy the equation. Well, first of all, let's look at the vertex, 3, 4. Well, when x equals 3, I have negative 2/9 times 0, so y equals 4. So the vertex certainly satisfies the equation. But I want to check these 2 points as well. One of the things we should notice here is that we're getting a y coordinate of 2 in both situations. And then when x equals either 0 or 6, I'm going to end up with 9 here. 0 minus 3 squared is 9, and 6 minus 3 squared is 9. So I'm just going to check one of these 2 points. So if x equals 6, then y equals negative 2/9 times 6 minus 3 squared plus 4, which is negative 2/9 times 9 plus 4, which is negative 2 plus 4, which is indeed 2. That's what I wanted. I wanted the ordered pair 6, 2 to satisfy the equation. Now I'm hoping that you notice that if I had just plugged in 0 here, I'd have 0 minus 3. Well, I'd still have 9, and I'd still get 2. So an equation for the parabola in Figure 1 is y equals negative 2/9 x minus 3 quantity squared plus 4. Let's try that again. Now I have a parabola that opens up. Can I read the coordinates of the vertex off the graph and use vertex form? Well, I can. I can see that the vertex occurs at negative 2, negative 5. So I know that y equals a times x minus negative 2, square that all, plus negative 5. Cleaning things up a little bit, I have y equals a times x plus 2 squared minus 5. Now I need to determine the value of a. All I know is that a is positive. So now, trying to find another point on the graph to use, I see I can't use the vertical intercept because I cannot read the second coordinate of that point off the graph. Well, let's look for some other points. I notice that one of the horizontal intercepts is 3, 0, so I'm going to use that point to determine a. So, since y equals 0 when x equals 3, I got that off my graph, I can solve the equation 0 equals a times 3 plus 2 squared minus 5. Solving for a, I have 0 equals 25a minus 5. 5 equals 25a, so a equals 5 over 25, or 1/5. So my proposed equation is y equals 1/5 x plus 2 squared minus 5. Remember, I expected a to be positive because my parabola is opening up. Now I want to check. First of all, checking the vertex. When x equals negative 2, this factor becomes 0. 0 minus 5 is negative 5. The vertex certainly satisfies this equation. Checking 3, 0 is another point on the parabola. If I look at the other x-intercept, negative 7, 0, that should satisfy the equation as well. Now, one of the things I want to point out is whether I replace x with negative 7 or 3, I'm going to have 25 for this square term. So I'm just going to check one of the points. So if x equals negative 7, I want my y value to be 0. Y equals 1/5 times negative 7 plus 2 squared minus 5, which is 1/5. Negative 5 quantity squared is 25. So I have 5 minus 5, which is indeed 0. So that second horizontal intercept also satisfies the equation. So I can conclude that an equation for the parabola graphed in figure 2 is y equals 1/5 x plus 2 quantity squared minus 5. Here's another mystery parabola. Can I use the vertex form? Well, let's look at the vertex. Problem in this situation is I cannot read the coordinates of the vertex off the graph, so I'm going to have to try something else. So this time I think I'm going to work with standard form. And the reason why I'm making this choice is because I can read the coordinates of the vertical intercept off the graph. I already know one value in my quadratic equation. I know that c should equal negative 5. Now these are like the problems Candace did at the beginning of this lesson. I need 2 more ordered pairs in order to determine a and b. Well, looking at that x-intercept, I can't read the first coordinate of that point off the graph. But fortunately, the second x-intercept is easy to read. The point 1, 0 is on this parabola. I just need one more point. And I see that the point negative 2, 3 is also on the parabola. So using these 3 points, I should be able to determine a, b, and c. So, starting off here, I know that c is negative 5. So I'm just going to put that into my standard form for the quadratic equation. Now, the ordered pair, negative 2, 3, tells me that y equals 3 when x is negative 2. And the ordered pair 1, 0 tells me that y equals 0 when x equals 1. So simplifying things here, I end up with the system 3 equals 4a minus 2b minus 5, and 0 equals a plus b minus 5. Adding 5 to both sides of both of these equations leaves me with 4a minus 2b equals 8, and a plus b equals 5. So now I have a system of two equations and two unknowns that I can solve for a and b. So now let's solve that system to determine a and b. So our system was 4a minus 2b equals 8, and a plus b equals 5. So let's solve this for a and b. I think here I'll use the method of elimination, and I'm going to multiply that second equation by 2. So my first equation is 4a minus 2b equals 8. Multiplying both sides of the second equation by 2 gives me 2a plus 2b equals 10. So solving the system, adding will eliminate the variable. I end up with 6a equals 18, so a equals 3. Now, when a equals 3, I know b equals 2, because I have the equation a plus b equals 5. I knew that c was negative 5, so it seems like my proposed equation will be y equals ax squared, that's 3x squared, plus bx minus 5. But let's check. So here's the graph we started with our equation. We want to perform a check. Well, one of the points that's very easy to check is the vertical intercept. So clearly, when x equals 0, y equals negative 5 in our equation. So I'm just going to check the other 2 points on our parabola. So here's my check. If x equals negative 2, then y equals 3 times the square of negative 2 plus 2 times negative 2 minus 5. 3 times 4 is 12, minus 4 minus 5, that's 8 minus 5, which is indeed 3. So the point negative 2, 3 satisfies our equation. If x equals 1, then y equals 3 times 1 squared plus 2 times 1 minus 5, which is 5 minus 5, which is 0. So 1, 0 satisfies our equation. So the ordered pairs on our parabola satisfy the equation we came up with. So an equation for the parabola in figure 3 is y equals 3x squared plus 2x minus 5. Now the reason why I'm saying this is an equation rather than the equation is we've seen that there's more than one form to write the equation of a parabola. We can use standard form like in this example, or vertex form like in the first 2. Let's do another one. Now when I find the equation of this mystery parabola, one thing I know for certain is that a will be negative because this parabola opens down. Can I use vertex form? Well, once again, I can't read the coordinates of that vertex off my graph. So I'm going to work with standard form. I need some points. Well, fortunately, we know the vertical intercept, so the c value will be easy to determine. I need 2 more points on the graph. The horizontal intercepts won't help me, but I do see the point 3,1 and the point 2,6 also lie on this parabola. So all 3 of these ordered pairs satisfy the equation. So I can use this to find a, b, and c. The point 0,4 tells me that c equals 4. So I know y equals ax squared plus bx plus 4. Using the ordered pair 3,1 gives me another equation. Y is 1 when x is 3. Using the ordered pair 2,6 gives me another equation. Y is 6 when x is 2. So I'm just substituting 6 for y and 2 for x in my standard form. So simplifying things a bit here, I have 9a plus 3b plus 4 equals 1, and 4a plus 2b plus 4 equals 6. Rewriting this system of equations so I have the constants on one side leaves me 9a plus 3b equals negative 3, and 4a plus 2b equals 2. Let's solve this system for a and b. So here's the system. I'm going to solve this using the elimination method. And I think I'm just going to choose to eliminate b. So if I have a coefficient of 6 in one equation and -6 in the other, I'll be able to eliminate b. So I'm going to multiply the first equation by 2, and I'll multiply the second equation by -3. So this leaves me 18a plus 6b equals -6, and -12a minus 6b equals -6. Adding these two equations will eliminate b, that was my goal, and I end up with 6a equals -12. So a equals -2. Now I need to determine b, and I can use either of my two equations from my system. I think I'll use the second equation. So if a equals -2, then I have 4 times -2 plus 2b equals 2. So 2b equals 10, and b equals 5. I knew that c equaled 4 from my original graph, so my proposed equation is y equals ax squared, so that's -2x squared, plus bx, that's plus 5x, plus c, which was 4. Let's check. Going back to the graph, I have my 3 points. I want to make sure all 3 satisfy the equation. The vertical intercept, when x equals 0, y equals 4, that's an easy check. Let's check the other 2 points. So we're going to start with 2, 6. So if x equals 2, then y equals -2 times 2 squared plus 5 times 2 plus 4. So let's see, I have -2 times 4, that's -8, plus 10, plus 4, which is indeed 6. So the ordered pair 2, 6 satisfies our equation. What about if x equals 3? Then y equals -2 times 3 squared plus 5 times 3 plus 4. This gives me -18 plus 15 plus 4, which is 19 minus 18, which is 1. Also, the point 3, 1 satisfies the equation. So we came up with the right equation for that parabola. The equation for the parabola is y equals -2x squared plus 5x plus 4. One last example. Here's our mystery parabola. Can we use vertex form? Well, in this case, indeed, I can read the coordinates of the vertex off the parabola. Now, vertex form's a little bit faster because we really just have to work to find a, because we know right off the bat that h is -4 and k is 3. So I'm just going to have to work to determine a. I just need some other point on the parabola. The vertical intercept's not going to work. The horizontal intercepts aren't going to work for me. But I see that the point 2, -3 is on the parabola. I'll use this to determine a. When x is 2, y is -3, so substituting 2 for x and -3 for y, I end up with an equation I can solve for a. So -3 equals 36a plus 3, subtracting 3 from both sides. -6 equals 36a. And when I divide both sides by 36, I end up with a equals -1/6. So my proposed equation is y equals -1/6 x plus 4 quantity squared plus 3. A is negative. Does my parabola open down? It does. To perform a check here, I also notice that the point -10, -3 is on the graph. By symmetry, I can see if I replace either x with either -10 or 2, I'm going to end up with 6, or the opposite of 6, squared here. So in both cases, I should get the same y value. I'll just perform that check. You can quickly check to see that the vertex does indeed satisfy this equation. So I'm going to check one of these 2 points, and I think I'm going to choose the point -10, -3. So if x equals -10, then y equals -1/6 times -10 plus 4 quantity squared plus 3. -10 plus 4, that's -6. -6 squared is 36. 1/6 of 36 is 6, so I have -6 plus 3, that's -3. So the ordered pair -10, -3 does satisfy the equation. You can quickly see why I'm not checking this point as well. If I drop in 2 for x, I'm going to have 2 plus 4, which is 2 plus 4 squared is 36. I'm going to get -3 there as well. So an equation for the parabola is y equals -1/6 x plus 4 quantity squared plus 3. So we're going to take just a minute to summarize our strategy. But before I do that, I just want to point out that it was just a coincidence that a was a fraction in all of these examples I did in vertex form. You may do some problems where you'll come up with an integer value for a as well. So given a graph of a parabola, if the coordinates of the vertex can be read off the graph, we can use the vertex form for the equation of a parabola. We plug in the values of h and k, and then we use a point on the parabola other than the vertex to determine the value of a. When all is said and done, we want to check that the points on the parabola do indeed satisfy the equation. If the coordinates of the vertex cannot be read off the graph, but the coordinates of the vertical intercept are known, we can use the standard form for the equation of the parabola. Why do we care that we can read the coordinates of the vertical intercept? Well, this gives us the c value. So the value of c is going to be the second coordinate of the vertical intercept. If we didn't know this, there'd just be more algebra involved, and we're going to postpone that question to intermediate algebra. But if we know c, then we just need to choose 2 more points on the parabola and write and solve a system of equations to determine the values of a and b. Finally, when all is said and done, we want to check that the points on the parabola do indeed satisfy the equation that we determined. So that's it for lesson 17.
1, 2, 3, 4.